Polynomials is a branch of mathematics. In the topic of polynomials, we are going to discuss various types of expressions like variables, constants which come into existence. But before that, let's see the introduction of polynomials. What are polynomials? How do we define them in mathematics? Is what is today's session. When we come to the introduction of polynomials, let me come with the basic properties or the formulae which you have learnt in the lower classes. To recap with the formulae as learnt in the lower classes, one of the most famous formula is a plus b whole square or x plus y whole square. So let's see how we can expand this. We all know that this expansion is a plus b whole square is a square, that is x square plus 2ab, which is this, and b square, which is y square. So x plus y whole square is derived to be x square plus 2xy plus y square. We all know this formula because we have applied in many concepts in the lower classes. Now next comes how this is related to the polynomial. So let's see how this is related to the topic of polynomials as introduction. As we see here, every expansion expressed in the form of variables is a polynomial provided its powers are all whole numbers. Now what is the power of x? For the first term, x square, the power is 2. Next, the power of x is 1 and the power of y is also 1, and next comes the power of y in the third term, which is 2. For this to be a polynomial, the condition is that each of the powers must be whole numbers, as whole numbers of the real number system. So if all the powers belong to the whole number, then that whole expression is called a polynomial. A polynomial with the powers being whole numbers is how we define for a basic definition of polynomial. Let's take one more example. For example, I have x plus y whole cube, and I can expand this. We all know that a plus b whole cube is a cube plus 3a square b plus 3ab square plus y cube. And let's see if this is a polynomial. Now the variables here are identified to be x and y. The variables of the polynomial are the unknown constants which accept any real number. So x and y are just representation of the real numbers in the real number system. So any polynomial can accept all real numbers is how we define for the variables x and y, or only x for the polynomial. So for example, if I have this, I have the power of this to be 3, the power of this 2, the power of this 1, the power of this 1, this 2, and this 3. And I notice that each of the variable has the powers which are whole numbers, and therefore this belonging to w makes the whole of the polynomial, of the whole of the expression given out here, to be a polynomial. Polynomial is defined through the powers of the variables. If the powers of the variables are whole numbers, then the expression is a polynomial. If the powers of the variables are not whole numbers, then the whole expression cannot be defined as a polynomial. Let's see an example which is not a polynomial to understand the concept more better. For example, I have, say, p of x. I denote the polynomial with, say, for example, p of x, which indicates polynomial in variable x belonging to R. Then if I have this to be 3 plus 5 by x plus 4x minus 5x squared, and let's see how each of the powers are out here. Now 3, which is a constant, can be written as 3 times of 1, which indirectly can be written as 3 times of x power 0. So I have my constant with indirectly the power of the variable being 0 because x power 0 or a power 0 is 1. And therefore 3 written as 3 times 1, 3 times 1 which is x power 0. Therefore indirectly I extract from a constant the power of the variable is assumed to be 0 for any constant in the polynomial or in the expression. Next, if I have phi over x, this can be written as phi times of 1 by x, which is x raised to negative 1. So phi over x is phi times x raised to negative 1. Therefore, I assume the power of x in the second term is negative 1. Similarly, I have my third term out here, which is 4x. Therefore, the variable x has the power 1. And therefore, I have 1 as the constant derived from the variable of the third term. Similarly, let's go to the fourth term. The fourth term has the power of x clearly seen out here to be 2, and therefore I just drop down 2 out here. Now let's check for each of the constants. I have the constant 0, minus 1, 1 and 2. Yes, this is a whole number, this is a whole number, this is a whole number, but this is not a whole number because minus 1 does not belong to W as discussed in the previous sessions. Therefore, since minus 1 does not belong to W, therefore the expression P of x given to be 3 plus 5 over x plus 4x minus 5x squared denoted by px is not a polynomial. It fails to be a polynomial because it's one of its integral power, one of its power of x does not belong to W, the whole numbers. Therefore, P of x is not a polynomial. Is how I identify the definition of a polynomial from the powers of the variables. In this case, x being the variable. Next, let's see the different types of polynomials. Now that we have defined what a polynomial is, let's classify the different types of polynomials existing in the branch of mathematics. Now, types of polynomials is the session. As we discussed about the definition of a polynomial, let's take, for example, a polynomial of one term. A polynomial can have any number of terms depending on the given problem. So what if it has one term? What if the polynomial has two terms or three terms or four terms or etc. and etc. So let's start with a polynomial which has one term. So let me take, for example, a polynomial P of x equals 4x. Surely this is a polynomial because its power is, the power of the variable is 1 which belongs to whole numbers. Therefore, P of x is a polynomial. Specifically, P of x is a polynomial of one term. There's only one term out here is what we need to notice. Now in this case, any polynomial which has one term has got its specific name, which is called a monomial. A monomial is a polynomial which consists of only one term. Let's take one more example. How many terms out here? There are two terms. But is this a polynomial? Yes, of course. The power of x is 1. Each of 1 belong to whole number. Therefore, this given expression in the given example problem is a polynomial, but this is not a polynomial of two terms because this can be further simplified. Like 14x minus 2x, which can be further simplified to get 2x. So we need to simplify this further to get the most simplified form, and the most simplified form of the given problem 14x minus 12x is 2x. So this is the actual polynomial which intends to be decided on. Now here, the power of x is 1. It belongs to whole number. It's a polynomial, and it is a polynomial of one term, and therefore this polynomial indirectly given by this is a monomial. So the learning outcome in this example problem is that when a polynomial is decided for a monomial or any other polynomial of more than one term, we try to decide on simplifying the given polynomial to the most simplified form, and then decide on the number of terms in the polynomial. The number of terms decide the definition of that particular polynomial. In this example, this being simplified to get 2x, and hence it's a monomial. Monomial is a polynomial which consists of only one term. So here I have the learning outcome which says monomial, it is a polynomial containing only one term. Is how we define the monomial, a polynomial with only one term. What if the polynomial is having only constant? Let's take an exceptional example in this case to decide, to understand the concept of monomial more stronger. For example, I have my function or the polynomial to be -3. Is this a polynomial is the biggest question before we decide on this polynomial being a monomial. So let's see if the given problem is a polynomial and then justify on that being a monomial. Clearly the function f of x here is given to be -3, and as we have discussed, -3 can be written as -3 times 1 because any number times 1 is that number itself. Now the reason why I multiply with 1 is to see that I can substitute this 1 with x power 0, because we all know that a power 0 equals 1, provided a is not equal to 0 is the condition. For a non-zero term, a power 0 is 1 for a not equal to 0 and for a belonging to R. So using that property, I have 1 which can be written as x power 0. So this is the polynomial indirectly for f of x. So that this is a polynomial because the power of x, which is 0, belongs to w, and thus satisfies the condition of the definition of a polynomial. So -3 x power 0 is a polynomial. So indirectly -3 is a polynomial, and it is a polynomial of one term because I have only one term out here, and therefore this is a monomial based on the definition of monomial is a polynomial containing only one term, and therefore is equal to -3 is a monomial. Is how I understand monomial as the definition of a polynomial with one term. Monomial is a polynomial of one term. The next type of polynomial after the discussion of monomial is binomial. So let's see what a binomial is in the branch of polynomials. As we see the word bi as taken from binomial, it clearly indicates that bi refers to 2, and monomial, which has mono, refers to 1, and therefore binomial refers to a polynomial of two terms. It's very simple that a polynomial which has one term is a monomial, and a polynomial which has two terms in its expression is called a binomial. Bi refers to 2 and mono refers to 1. Is how we understand the definition of a binomial in the most simple manner. For example, if I take the polynomial p of x equals 3x minus 5x cubed. Now this expression clearly is said to have two terms, and let's see if this is a polynomial. To start with, the variable has the first term of the variable x has its power which is 1, and the second term has its power which is 3. The power of x is 1 and the power of x is 3, and we know that 1 and 3 both belong to whole numbers, and therefore by the definition of a polynomial, this is a polynomial. Now exclusively, this is a polynomial of two terms, the first term being 3x and the second term being negative 5 times of x. So a polynomial which has two terms, which is bi, hence a binomial. Therefore, since p of x has two terms, 3x and minus 5x, therefore p of x is a binomial, is how we understand the definition of a binomial using the properties of the polynomial. The next type of polynomial which we are going to discuss in the session is trinomial. Monomial, a polynomial of one term; binomial, a polynomial of two terms; trinomial, a polynomial of three terms. It's as simple as it is written out here. Trinomial. Tri refers to 3, and hence trinomial is a polynomial of 3 terms. This is how we understand the definition of a polynomial. For example, if I have p of x let's see if this is a trinomial or a monomial or a binomial. So in order to do an example problem of this sort in identifying for the type of a polynomial, we first try to simplify. As the condition says, the polynomial has to be in the most simplified form before we justify for that polynomial being of the 3 types. So let's try to simplify this polynomial before we justify on the trinomial case. So we need to first expand this, as we know that in the lower classes what we have learnt, we expand first 5 with this, and then we expand x with this. So each of the term of the first bracket is multiplied with the terms of the second bracket. That is how we understand the multiplication of two factors or two expressions. Now, as we multiply first 5 with this and x with this, then on further multiplication of 5 to each of the terms, 5 times this and this and this, and each of this multiplied to this, we come across 5 times 3 first, which is 15, then 5 times of x for the second term being 5x, and then 5 times of x square, which is 5x square, then x times of 3, which is 3x, and x times of x, which is x square, and x times of x square, which is x cubed, is how we understand the multiplication of each of the terms when expanded through the brackets. Let's try to further simplify this. As we see that this can be more further simplified by taking the constant here and then by pairing all the terms x one side together, and then I get this to be 5x plus 3x, which is 8x, is how we understand, and then minus 5x squared plus x squared, which is minus 4x squared, and then I get this to be minus x cubed. That's it. And I cannot further simplify this. This is the end of the polynomial. Now clearly I see that this polynomial, let's see if this is a polynomial. The power of x here is 0, and the power of x here is 1, and the power of x, the variable x, is 2, and the power of the variable x here is 3. Therefore, each of 0, 1, 2, 3 belong to the whole numbers, and therefore this is a polynomial. This polynomial has 4 terms, but a polynomial of 3 terms is a trinomial. Therefore, this cannot be a trinomial. the given example problem is not a trinomial. For a trinomial, the most simplified form must be of 3 terms. So here we conclude saying that this is not a trinomial. Is how we understand the concept of trinomial and not a trinomial. Let's take one more example to see if that is a trinomial. For example, I have this to be f of x equals 5 plus x minus 4x squared. Yes, in this case, the power is 0, the power is 1, the power is 2, and therefore all 3 belong to W, and hence because it has 3 terms, the first term being 5 and the second term is x and the third term is minus 4 times x raised to power 2, therefore it has 3 terms, and since it has 3 terms, it's a trinomial, a polynomial of 3 terms. Therefore f of x is a trinomial. It's a trinomial is how we conclude. Binomial, trinomial, and monomial is what we discussed as the different types of polynomials. Now let's take an exceptional problem and identify if that is a trinomial or a binomial or a monomial. For example, I have f is from x to x squared minus 3x plus 5x power minus 2. So let's see what kind of a polynomial or whether it's a polynomial or not. Now clearly I see that there are 3 terms, but I can call this to be a trinomial, but no, this is not a trinomial, because for a trinomial initially it needs to be a polynomial. So for the first term I see my power is 2, and for second time my power of the variable is 1, and for this my power of the variable is minus 2. 2 and 1 belong to whole number, but minus 2 is not a whole number. Since minus 2 does not belong to W, therefore it fails to be satisfying the definition or the rules to be defined for a polynomial. And therefore, with this rule breaking up, I say that the given function, therefore f from x to x squared minus 3x plus 5x is not a polynomial, and hence is not a trinomial. Therefore, the condition for the given expression to be a type of a polynomial is that it needs to be a polynomial itself initially. So this is not a polynomial and hence not a trinomial, is how we conclude the given example problem. Next, let's discuss about the types of polynomials which are in 1 variable and 2 variable. That is, we're going to discuss about 1 variable polynomial and 2 variable polynomial or a 3 variable polynomial. In order to discuss that, let's classify the types of polynomials into 3 types. The first one is 1 variable polynomial. The second is 2 variable polynomial, and the third is 3 variable polynomial. So let's see each of the classifications of the types of polynomials: 1 variable, 2 variable, and 3 variable. So in this, as we have discussed, if the polynomial has only 1 variable, say for example, I have p of x is equal to 5 minus 3x plus 4x squared, then in this case the variable is only 1 variable. Therefore, such a polynomial which has only 1 variable x is called a 1 variable polynomial. What is a 2 variable polynomial? It concludes in the same manner as we have defined for 1 variable polynomial. That is, if I have 2 variable polynomial generally denoted by p of x comma y, then we clearly identify that there are two variables x and y in case of the polynomial px comma y. For example, if I take a polynomial of the form pxy is equal to x square plus xy plus y square, then this is a trinomial of two variables, or a polynomial of two variables x and y. Here the variables being x comma y on the right hand side expression. So this comes to be a two variable polynomial. Next, let's see a three variable polynomial, followed by the two definitions coming from one variable to two variable and then three variable. It is quite obvious that a three variable polynomial would be defined as px, y and z. The three variables identified here are x, y and z. And for example, if I take a polynomial to be 3 minus 5x plus 4yz plus 2x square z cube, then I say this is an example of a three variable polynomial because it has three variables x, y and z. And interestingly, all these three are polynomials because they satisfy with the condition that the power of x here is 0 and the power of x here is 1 and the power of x is 2, which belong to whole number. And coming to the second example, the power of x is 2, the power of x is 1 and y also is 1 and the power of y is 2. So each of the powers of x and y taken independently are nothing but whole numbers, and hence the whole expression here is a polynomial of two variables x and y. Let's see the third polynomial of three variables. The power of 3 is 0, the power of x is 1, the power of y is 1 and the power of z is 1 and power of x is 2 and z is 3. As we see independently 0, 1, 1, 1, 2, 3, all the numbers belong to whole numbers. They all belong to W, and therefore this whole expression is a polynomial of three variables x, y and z. Two variable, one variable and three variable polynomials are the types of polynomials in the branch of mathematics. Next, degree of a polynomial. Let's see what is the degree of a polynomial in the branch of polynomials. Degree. Let's see what exactly the degree is by taking an example problem. For example, I have a polynomial p of x denoted by 3 minus 5x plus 4x cube minus 7x power 9. Now this is a polynomial of 4 terms, and clearly I see each of the powers of x are whole numbers, therefore it must definitely be a polynomial. It is a polynomial of 4 terms, and let's see what the degree is for this polynomial. The polynomial degree is generally denoted by degree of p of x is how we define, and this is nothing but the highest power of x. So degree of p of x in the most simple language is defined to be the highest value of the power of the variable. So what is the highest value of the power of the variable? As we take in this example problem p of x, which is 3 minus 5x plus 4x cube minus 7x raised to 9, I see that the power of variable x here is 0, the power of variable x in the second term is 1, and the power of variable x in the third term is 3. and the power of variable x in the fourth term is 9. So each term has its own variable value. Now here the first term has the power of x 0, the second term with 1, the third term with 3, and the fourth term with 9. Now the definition comes: the degree of the polynomial, the whole of the entire polynomial, is defined to be highest value of the power of the variable. Now which is the highest value of the power of the variable? We select the powers, and finally I find this to be the highest. This is the highest, and hence this is the degree of the given polynomial. Is how we understand the degree of the polynomial p of x. Therefore, degree of the given polynomial p of x is 9. Is how we understand in the most simple language. Let's see one more example to understand the concept more stronger. For example, I have p of x is equal to 7. Is it a polynomial? Yes, it is a polynomial. It's a polynomial which is called a monomial because this polynomial has only one term, that is 7. So it is a monomial with its highest power being 0, because this can be written as 7 times 1, 7 times x power 0, which comes out to be 0. So the power of the variable x here is 0, which belongs to w, and hence it is a polynomial. But as you see the definition, the highest value of this entire expression is nothing but the power of the variable x here itself, because there's only one term, and hence degree of p of x is 0. The given polynomial is 0. So what do we understand with this standard example out here? For any constant polynomial, that is a polynomial which is expressed as a constant, its degree is always 0, is the most important learning outcome with this example problem. Therefore, every polynomial which is a constant, or I call this as every constant polynomial, has degree 0, is the learning outcome which I make in this example problem. If a polynomial is a constant polynomial, just like p of x equal to 7, then its degree must be 0. It cannot have other than the value 0. Now let's see the coefficients of a polynomial. Now that we have discussed about the degree of a polynomial and the types of polynomials, now comes the question which raises on what would be the constants called in a polynomial. The variable x has its own definition. Similarly, the constant attached to that variable also has its own definition. For example, let's start with coefficients of polynomial. For example, I take the polynomial function p of x is equal to 4x cubed minus 3x squared minus 7x plus 9. Now in this case, it is a polynomial with 4 terms and it has the degree 3 because the highest degree here, or the highest value of the power x, is identified to be 3. So the degree of this polynomial is 3, and it is a polynomial consisting of 1, 2, 3 and 4 terms. Now let's see what are the coefficients. So coefficients for a polynomial are generally the constants which are multiplied or attached to the given variables or to the variables raised to any power. Here I identify the coefficients to be, for x cubed I have a constant 4 which is attached, and for x squared I have the constant attached which is negative 3. Even the sign takes into account. It's important that we take even the negative sign into account. For coefficient of x, the constant attached to x is -7 and the constant independent separately is 9. Therefore, here in this example problem, I identify that the coefficients of the polynomial p of x are 4, -3, -7 and 9 is how we identify the coefficients of the given polynomial. The coefficients are 4, -3, -7 and 9 for this given polynomial. Coefficients are the real numbers, constants or the real constants attached to the variables is how we identify the coefficients for a polynomial. Now let's see some special type of polynomials in the topic of polynomials. The types of polynomials have their own types which we have discussed, but now let's enter into discussing the special types of polynomials. Zero polynomial plays a very vital role in the branch of mathematics. Though its significance is learnt in higher classes, let's discuss its definition as a special case. Special type of polynomial. Let's see what zero polynomial is defined in the topic of polynomials. A polynomial which equals to 0, a constant polynomial whose constant is 0. We know that a constant polynomial is a polynomial which just has its k belonging to R is called a constant polynomial, k being any real number. If that real number is exclusively the value 0, then this polynomial is called a zero polynomial. Is how we define the zero polynomial with its own definition. P of x equals 0 is called a zero polynomial. Now the coefficient of a zero polynomial is not defined because anything multiplied with 0 is 0. So we have the coefficient itself being 0, so we take it as an exceptional case and hence it is a special type of the polynomial, which we're going to learn in higher classes. So zero polynomial is the constant 0 itself. What is its degree? The degree of a constant polynomial is 0 and hence the degree of the zero polynomial is also 0. Is 0. And moreover, because it has only one term, a zero polynomial is sometimes called a zero monomial. It is also called sometimes a zero monomial because p of x equal to 0 has only one term which is 0. Therefore, I can call the zero polynomial as a zero monomial with degree 0. Is how we understand the concept of the polynomial as a special case, with zero polynomial being a special case of the polynomials. Now let's see the polynomials which are classified through its degree value. Now that we have discussed about degree of a polynomial, let's now enter into taking the same degree definition into classifying the polynomials based on its degree value. Classification of polynomials based on its degree value is what we're going to discuss in the session. For example, I take a polynomial p of x which is 4x minus 5, then I clearly see that with this example problem p of x equals 4x minus 5, I have this to be, I have my p of x, which is 4x minus 5 with degree equal to 1, because the highest power of x here is 1, and for this it is 0, and the highest power being 1, degree is 1. Therefore, p of x, whose degree is 1, is given by the special name called linear polynomial. Any polynomial whose degree is 1 is defined to be a linear polynomial, irrespective of the number of terms existing. Next, let me take one more example. P of x is equal to 5x squared minus 4x plus 9. Now this polynomial has 3 terms. Let's see what exactly is the degree for this polynomial. When I take with the first term, the highest power is 2, and when I take with the second term, the power is 1, and when I take the third term, the power is 0. And therefore, when I decide on the highest value, 2 is the highest value, and therefore degree of p of x for this example problem is 2. So for this example problem, the degree is 2. And any polynomial whose degree is 1 is called a linear polynomial. Similarly, any polynomial whose degree is 2 is called a quadratic polynomial. Is how we define with degree 1 linear polynomial, with degree 2 quadratic polynomial, and degree 3 is what polynomial is what next we are going to investigate. So what is the name of the polynomial whose degree is 3? So let's take an example. Let's identify the degree. The power of x here is 0, the power of x is 1, the power of x is 3, and the power of x is 2. And deciding on the highest value, 3 is the highest value. And therefore, for this example problem, degree is 3. And because the degree is 3, this polynomial is given by the name cubic polynomial. Cube stands for 3, quadratic stands for 2, linear stands for 1. So degree 3 stands for cubic polynomial. Is how we define the different types of degrees, defining the different types of polynomials. Degree 4 and degree 5 to be discussed has, if the degree is 5, if the degree is 4, then the polynomial is called quartic polynomial. And if the degree is 5, the polynomial is called quintic polynomial. This is out of the syllabus, but just for presumed knowledge, this degree 4 makes us quartic polynomial. Degree 5 makes a polynomial to be called a quintic polynomial. Linear, quadratic, cubic, quartic, quintic, etc. is how we define the polynomials classified based on its degree value. Now that we have discussed about the different types of properties which lead to understanding the polynomial more better, let's enter into solving some problems where I need to find the value of the polynomial at a particular value of the variable. Now, as the variable is a real number which can accept any real number, now my question comes, if I give a fixed value of the real number for that given value of x, what would be its respective polynomial value? So let's see in today's session about the polynomial value identified for the value at x. Polynomial value at a specific value of x belonging to the real numbers. is what we are going to discuss here. So for example, I have a polynomial p of x equals x squared minus 4x plus 6. Of course, this is a quadratic polynomial because its degree is 2, and it is also called a trinomial because it has 3 terms. Is how we define with the recap of all the properties we have learned. Now for this example problem, p of x equals x squared minus 4x plus 6, let's see what is its polynomial value at the question. For p of x equal to this, find p of x at x equals minus 1. So my question out here is, find the value of this polynomial at a specific value of x equals minus 1. So let's see how we can simplify. The given polynomial or the trinomial p of x is x squared minus 4x plus 6, and I need to find p of x at x equal to minus 1. So to find p of x at x equal to minus 1 implies I need to just find p of minus 1. The notation for finding p of x at x equal to minus 1 is defined as p of minus 1 because simply this value of x gets replaced with x, and therefore p of x changes to p of minus 1. And p of minus 1 is p of x being x squared minus 4x plus 6 when x is moved out and minus 1 is moved in. Similarly, each of x is moved out on the right side and each of minus 1 is moved in the respective places. Therefore, at x I get minus 1 whole square. At x here I get minus 1 and plus 6. So each of the x is being replaced with each of minus 1 equally on the right. Because it is being replaced with minus 1 on the left side, I equally replace on the right hand side, is how I understand this property. When I simplify this further, I get this to be minus 1 whole square, which is 1, minus 4 times minus 1, which is plus 4, because minus into minus is plus, and then comes plus 6. This, on further simplification, gives 6 plus 4, which is 10, 10 plus 1, which is 11. Therefore, p of x at x equal to minus 1 is understood as p of minus 1, which is more understood to be simplified with the value 11, is how I understand the polynomial value at a specific x belonging to R. In this case, the specific x being minus 1 through this example problem. So polynomial value can be found for that specific value by simply substituting that specific value in place of the variable x in the polynomial, as seen in this example problem. The next important definition in the continued session of polynomials is zeros of a polynomial. It is very important to understand the definition of zeros of a polynomial. So let's see in today's session about zeros of a polynomial. So in general, the word zero is coming into existence in this topic of zeros of a polynomial. So it has got definitely to do something with 0. Let's see how the definition comes more brief. Let me take the polynomial p of x. Now, zero of a polynomial is defined as zero of a polynomial p of x. Say for example, for p of x, the zeros of a polynomial p of x are the values of x for which this equal to 0. This is the main condition which makes us extract the value of x, and that x is called 0 of a polynomial. Let's see it more brief. The zeros of the polynomial p of x are defined as the values of x for which p of x equal to 0. So in order to find the zeros of the polynomial, we simply simplify this equation p of x equals 0, and then those values of x which are obtained are called zeros of the polynomial. Let's understand this concept more stronger by taking an example problem. This is the definition. Let's take an example problem. For example, I have my polynomial p of x is x squared minus 5x plus 6. It's a quadratic polynomial or a trinomial, x squared minus 5x plus 6. Now I want to find the zeros of this polynomial. Therefore, I go with this definition which says that in order that I find the zeros of this polynomial x squared minus 5x plus 6, I just take this equation and solve. So let's see how it is possible. The given polynomial, for zeros of the polynomial p of x, the condition says p of x must be 0. So for zeros, the condition is p of x equal to 0. Indirectly, the p of x being replaced with the given expression in the problem, that is p of x is x squared minus 5x plus 6 equals 0. And this, on further simplification, we know that this can be factorized using the quadratic factorization, and then x squared minus 5x plus 6 can be factorized to be x minus 2 times x minus 3, which is equal to 0, which on further simplification gives us, when the product of two factors is 0, this is 0 or this is 0, and which on continued further gives me the value of x is 2 and x is 3. Therefore, for this expression, zeros of the polynomial or the values of x for which this is 0. So taking p of x equal to 0 with the given expression equated to 0, I get the two values of x, which are 2 and 3, which are the zeros of the given polynomial p of x. Therefore, zeros of the polynomial p of x equals x squared minus 5x plus 6 are 2 and 3 is how we define the zeros of the given polynomial. X squared minus 5x plus 6 are 2 and 3. 2 and 3, the zeros for the given polynomial, is how we understand the definition. Equate the p of x to 0, find x, and that x is the 0 of the given polynomial p of x. It's simple. Now let's take an exceptional problem where I need to find for a constant polynomial the zeros. The zeros of a zero polynomial is what we're going to discuss in today's session. Zeros of a zero polynomial is the exceptional case which we're going to discuss in the session. Let's revisit the zero polynomial which we have defined as a polynomial which has the constant 0. So for this zero polynomial, I need to find the zeros, which itself says that the zeros of a polynomial is the values of x for which p of x equal to 0. Now the polynomial being the zero polynomial being the p of x equal to 0 itself, I have all x belonging to R. For all x belonging to real numbers, the zero polynomial does not lose its definition. It must be p of x equal to 0. Therefore, for every x belonging to R, p of x is 0, or for any x replaced with any real number, I get the value to be 0. Therefore, zeros of the zero polynomial are all real numbers is how I understand the zeros of the zero polynomial are all real numbers. Every real number when substituted in x for p of x gives me 0, and therefore zeros of the zero polynomial are all real numbers. Infinitely many real numbers belonging to R. In this session, we are going to discuss about the different terminologies used for zeros of a polynomial. As we know that the zeros of the polynomial are the values of x for which the function or the polynomial is equal to 0, we also have different names through which we understand the zeros of the polynomial. So let's see the different notations and the terminologies used in understanding the zeros of a polynomial. Zeros of a polynomial are also understood as roots of a polynomial, and they're also understood as solutions of the polynomial. Of a polynomial. These are the different ways through which we understand the zeros. If I want to find the roots of the polynomial, it is nothing but indirectly referred to finding zeros of the polynomial. If I want to find the solution of a polynomial or solve the polynomial, it is nothing but indirectly finding the zeros of the polynomial. It's how I understand the different terminologies used. Different terminologies for zeros of a polynomial. Is how I understand the different terminologies for zeros of a polynomial. Zeros are the roots, are the solutions for a given polynomial p of x with variable x. Now, as a specific case, let's take the special case of a linear polynomial. In order to find the zeros of the linear polynomial, we have always identified that a linear polynomial has only one zero. Let's try to investigate the linear polynomial with an example problem. When coming to the linear polynomial, and with zeros, let's try to investigate on the zeros of a linear polynomial. For example, I take the linear polynomial p of x is 4x minus 8 or 4x plus 8, and I want to find the zero of this linear polynomial which has degree equal to 1. So in this case, what I do is, in order to find the zeros of this polynomial, for zeros of p of x, the condition is p of x equal to 0. We know that as the basic definition. So for zeros of this equals 0, must be equal to 0. And then p of x indirectly out here is 4x plus 8, which is equal to 0. And 4x plus 8 equal to 0 implies minus 4. So I get this to be minus 2. Therefore, the zero of this linear polynomial is minus 2. So this is the zero. Is how we identify the zero of the linear polynomial. But interestingly, I also note a very important property here, that for every linear polynomial, there is only one zero, is how we conclude. So let's make the overall outcome, which says that every linear polynomial has one and only one zero is how we come through the learning outcome, is how we make the learning outcome, which says every linear polynomial has one and only one zero. It cannot have two zeros. A quadratic polynomial may have two zeros, or at the most may have two zeros or less than two. A cubic polynomial has at the most three zeros or less than three. It cannot have four zeros. A quartic polynomial cannot have five zeros, but at the most can have four zeros. A quintic polynomial can at the most have five zeros, but not more than five. Is how we make the learning outcome through this investigation. Next, we are going to enter into the concept of understanding remainder theorem through the definition of polynomials and the various properties of polynomials. How does polynomials lead to understanding remainder theorem? But before we understand the remainder theorem, which plays a very vital role in the branch of polynomials, let's see how the divisibility concept is essential to understand the remainder theorem. We need to understand the divisibility concept in brief before we try to enter into the theorem called the remainder theorem, the most significant theorem in polynomials. Divisibility. Let's try to understand the divisibility properties by taking a very simple example. For example, I have a number 5 divided by 3. I would like to divide a number 5 with 3. So here I understand that the number which is being divided by is called dividend. The term which I give for a number which is being divided by the other number is the dividend, and the number which acts in the division is the divisor. So this plays a role in dividing, because 3 gets divided, it is called the divisor. Now when the number is divided, we have learnt in the lower classes, the method of division is through this, wherein 5 divided by 3 is written out here, and then 3 ones are 3, which on subtraction gives me 5 minus 3, which is 2. This cannot be further simplified because this number is less than this. So we halt it here and we call this as remainder. And this is given by specific name called quotient, and 5 is called the dividend and 3 is called the divisor. So the remainder, the quotient, the divisor and the dividend play a vital role in getting connected to each other. So each of these have their own properties, but they have their own mathematical relation connected, which says that the dividend, which is 5, as seen in this example problem, clearly is divisor times of quotient, which is 1, plus the remainder, which is 2. In every division concept, it holds true that the dividend is equal to the divisor times the quotient, that is 3 times 1 plus the remainder, which is 2, because this finally leads to 3 plus 2, which is equal to 5, which equals the dividend, is how we understand. Therefore, the divisibility property says if a number A is divided by B, that implies the dividend, which is A, is divisor times the quotient plus the remainder, is how we understand the divisibility property. Dividend is divisor into quotient plus remainder. dividend is A and divisor is B, is how we get. And more importantly, the remainder always lies and it is less than divisor, is very important property which gets connected through this. Dividend is divisor into quotient plus remainder, and the remainder can never exceed divisor and it is always positive. So 0 less than or equal to remainder less than divisor is how we understand the divisibility properties connecting the divisor, the dividend, the quotient and the remainder. Now the divisibility properties, let's connect with polynomials. So this session is about connecting the divisibility properties as learnt in the session with polynomials. What happens when we divide a polynomial with the other polynomial? If it is numbers, we have the concept through numbers, but if it is polynomials, we have the same concept as learned through polynomials. So today's session is about divisibility properties connected with polynomials. So let's see how we get the divisibility property through the polynomials. Say for example, I have P of x when divided with Q of x, the quotient f of x divided by g of x, the quotient is say Q of x and the remainder is R of x. That is, when I divide g of x polynomial with the function f of x, then I get my quotient which is Q of x, and then I get my R of x which is the remainder, is how we understand the divisibility connected with polynomials. And interestingly, here the property says dividend is divisor into quotient plus remainder. Therefore, using this divisibility property, which is called division algorithm, let's try to see how the polynomials get connected respectively. Dividend in this case being the polynomial which is being divided is equal to the polynomial which gets divided into Q of x plus R of x, is how we understand, provided with the condition that 0 less than or equal to the remainder less than the divisor, which is g of x, is how we understand the division algorithm for the polynomials f of x by g of x, or f of x divided by g of x. Divisibility properties connected with polynomials f of x and g of x. Now the continued session is about finding the remainder when a polynomial is divided by another polynomial. So this session will discuss about how we can find the quotient and the remainder for the polynomials which are divided with each other. To start with, finding the remainder. Let's take some example polynomials for understanding this concept more better. For example, I have a polynomial P of x, which is x cubed plus 3x squared plus 3x plus 1, which is divided by another polynomial x plus 1. And I would like to find the quotient and the remainder for this polynomial P of x being divided by another polynomial x plus 1. As we know that the long division method for dividing the polynomials is with the dividend taken in the middle x cubed plus 3x squared plus 3x plus 1, and the divisor which is taken on the left is how we start with the construction process. Now continuing with this, I have x cubed which can be filled up by multiplying x with x squared, so that I get x times of x squared, which is x cubed, and 1 times of x squared, which is x squared. And then I subtract with the change of signs, this get cancelled, and I get this to be 3x squared minus x squared is 2x squared, with the other two terms drop down directly from the given expression. Continuing in the same process, I have 2x squared which can be satisfied by multiplying x with 2x. So the quotient gets added up with 2x, which when multiplied with x gives me 2x squared plus 2x. And then on further subtraction in the same process gives me with change of sign 2x squared and 2x squared getting cancelled, and 3x minus 2x is x plus 1. So finally this is the term where I end up, because I don't have any other term, or I can take plus 1, so that 1 times of x is x and 1 times of 1 is 1, which on further subtraction gives me the change of signs and then cancel to give me the final answer as 0. So with the end of this, I understand that this is my q of x and this is my r of x. Is how we identify the remainder and the quotient for the given polynomials divided with each other. The long division method is what we call this. Therefore, for the given polynomial p of x equals x cubed plus 3x squared plus 3x plus 1, when divided with the other polynomial x plus 1, I get my quotient q of x is x squared plus 2x plus 1, and I get my remainder r of x is 0. Is how we understand the process of finding the remainder or the quotient using the long division method. Now that we have discussed about division of two polynomials f of x by g of x, it's very important that we just divide a polynomial with the other polynomial through a condition. Let's see what the condition for divisibility of two polynomials is out here, along with the division method of dividing the polynomials as we have seen in the previous session. Condition for divisibility of polynomials. Condition for divisibility of polynomials. Let's see how the condition exists for two polynomials being divided. So for example, I have a polynomial f of x which is divided by another polynomial, say g of x. Then the divisibility condition says that this polynomial can be divided by this polynomial provided we have degree of f of x is greater than degree of g of x. Is how I see the condition for existence of divisibility of two polynomials. Is how I see the condition. Condition for divisibility of two polynomials is only possible when degree of f of x is greater than degree of g of x. For example, if I take a polynomial 2x cubed plus 5x minus 2 by x power 7 minus 4, then clearly I see that the degree of this polynomial in the numerator is 3 and the degree of the polynomial in the denominator is 7. Therefore, I don't have my condition which satisfies here, because clearly in this case degree of the numerator is less than degree of the denominator. In this case 3 less than 7. Therefore f of x cannot be divided with the polynomial g of x in this case of the example problem. F of x can be divided with the polynomial g of x only when degree of f of x is greater than degree of g of x, and the division is done through the long division method as discussed in the session. Now that we have discussed the divisibility properties for the polynomials, now comes the most important theorem in the branch of polynomials called the remainder theorem. Remainder theorem helps us mostly in finding the remainder when a polynomial divided by another polynomial. You can directly use the theorem to find the remainder without constructing to the long division method. So let's see what the remainder theorem says in its own definition. Remainder theorem. As the theorem says, remainder theorem, this theorem dedicates in identifying the remainder of a polynomial divided by another polynomial. Is the first thing which we note from the theorem called the remainder theorem. Something relates to the remainder indivisibility. If I take a function f of x with the condition that the degree of f of x, the degree of the function f of x is not equal to 0, then let's see what the definition says or what the theorem states for this function f of x. So with the first condition that I take the polynomial f of x with degree of the polynomial f of x being non-zero, then in that case, that is, f of x is not a constant polynomial. In exception to the constant polynomial, if the function or the polynomial f of x is divided by x minus a. Now we all know that this is a linear polynomial because the power of x is 1, and hence this is a linear polynomial with the condition that a is a constant or a real number. So my theorem says that if a polynomial f of x whose degree is non-zero is divided by a factor x minus a or divided by a linear polynomial x minus a with a belonging to set of real numbers, then remainder of f of x denoted by capital R is nothing but f of a, is how I understand the theorem, remainder theorem in its own definition. Here we have the remainder, which is directly the polynomial in which the value a is substituted, and a is nothing but derived from the linear polynomial. For a polynomial f of x with degree being non-zero, if divided by a linear polynomial x minus a for a belonging to any real number, then the remainder of the polynomial f of x is directly f of a, is how the polynomial is related to the constant of the linear polynomial in the divisibility, is what the remainder theorem states. Now let's see an example problem to understand the remainder theorem more better. Let's try to apply the remainder theorem in real life. So coming to the remainder theorem, we have already defined that for any polynomial divided by a linear polynomial, then the remainder is directly connected to the factor of that linear polynomial into the polynomial. So we are going to use that theorem concept when we do certain problems related to remainder theorem. For example, if I have my question which says find the remainder when the polynomial f of x or p of x, when the polynomial p of x equals x cubed minus 3x squared plus 4x minus 1 is divided by x plus 2 is the question. The question is very clear about finding the remainder when the polynomial, which is x cubed minus 3x squared plus 4x minus 1, is divided by the linear polynomial x plus 2. So let's see how the remainder theorem can be applied for this particular example problem. As the polynomial is given to be p of x is x cubed minus 3x squared plus 4x minus 1, the first thing I identify is that this polynomial is not a constant polynomial. The first condition for remainder theorem is that degree of p of x should not be equal to 0. And clearly the degree of p of x is 3, and hence 3 is non-zero. Therefore, it satisfies with the first condition of the remainder theorem. Secondly, the second part of the given question is about the linear polynomial. Therefore, the given linear polynomial is x plus 2. And if I compare this with x minus a as given in the theorem statement, I clearly see that when I express x plus 2 in x minus a form as given in the remainder theorem, I have this x plus 2 which can be written as minus of minus 2. I extract minus out of plus, then one minus sign remains inside the bracket, so that minus into minus is plus, which retains back x plus 2. So the reason why I write this in this form is to extract in the form x minus a. So this a is nothing but the minus 2. Therefore, I have my a, which is minus 2, belonging to the real numbers. The constant, the non-zero constant a, is minus 2 in case of this problem. So this is the step 2 of identifying a. Step 1 of satisfying the condition of degree of p of x being non-zero, and step 2 identifying the value of a, and step 3 is finding the remainder itself. Now, for the polynomial p of x, when divided by x plus 2, the remainder is f of a, or p of a, or this is p of minus 2. This is strictly by remainder theorem. Remainder theorem clearly says that when a polynomial which is non-zero degree is divided by a linear polynomial, the remainder is f of a or p of a. And in this case, a being minus 2, it is p of minus 2. Without any long division method process, we can directly find the remainder using remainder theorem. So let's see how the remainder can be evaluated for this p of minus 2. Therefore, when I evaluate this, I get the remainder, which is p of minus 2, and p of minus 2 is the value which is obtained by substituting the value of x equal to minus 2 in the given polynomial p of x. Therefore, when I have p of x replaced with x being replaced with minus 2, equally the x gets replaced with minus 2 on the right side. So I have this to be minus 2 whole cube minus 3 of minus 2 whole square plus 4 times minus 2 and minus 1 is what we get when we expand by substitution of x equal to minus 2 on the right side of the given polynomial. When this is further simplified, I get this to be minus 8 minus 3 times of minus 2 whole square, which is 4, and minus 8 and minus 1. And this comes out further minus 8, minus 12, minus 8, minus 1. which on simplification gives 12 times 8, 20, 20, 12 plus 8, 20, 28, 29, which comes out to be negative 29. Therefore, I get the value of remainder for the given polynomial. Remainder of p of x is minus 29 is what I get finally using the remainder theorem. Remainder theorem helps me in finding the remainder when a polynomial is divided by a linear polynomial with the conditions out here. Continue. Now let's see how we can verify the remainder theorem using the long division method, because this is the property which we have used directly through the remainder theorem, which states the remainder is directly f of a or p of a, for x minus a being the divisibility polynomial. So here we're going to see the verification process whether we really get the remainder to be minus 29 when we just solve through the long division general method. So I have the polynomial, the dividend out here, and the divisor, which we're going to take at this thing. Dividend and the divisor, which when divided gives me x cubed minus 3x squared plus 4x minus 1 when divided by x plus 2. Let's find the quotient and the remainder, most importantly, to verify for the remainder as obtained through the remainder theorem. So as we know through the long division method, as discussed in the previous sessions, x times x squared gives me x cubed. 2 times x squared is 2x squared, which on subtraction gives me this cancelled, and I get this to be minus 5x squared plus 4x minus 1. I just drop in these two down here. Now the next second division method says my x when multiplied with minus 5x gives me minus 5x squared, and hence I just put in minus 5x squared in the quotient, so that this multiplied with this gives me the equal term as in the top, is how we understand the long division method. 2 times of minus 5x is minus 10x, and then when I subtract again, the signs change and this gets cancelled. Plus and minus of the same sign get cancelled, and that is the intention why I make the terms equal through the quotient by adding or subtracting the terms. 10 plus 4 is 14x minus 1. Minus 1 dropped straight down. Now this has to be made equal with x. So obviously it is 14 which is multiplied with x. Therefore my quotient gets added with 14. So that 14 times of x is 14x plus 14 times of 2, which is 28. Again using the same process of subtraction, the signs change and this get cancelled, and minus 1 minus 28 is minus 29, which is the remainder, which is the quotient. And most importantly, when I see the remainder as done through the long division method, I get the value as minus 29, and when I use the remainder theorem with its own statement, I get the value of remainder, which is minus 29, and hence they are same, which concludes that my remainder theorem is very much true to its best. Remainder theorem is most important in finding the remainder of the polynomial's divisibility. Now that we have discussed about remainder theorem and its significance in finding the remainder in dividing the two polynomials, let's try to take that concept more further. Remainder theorem also helps us not only about finding the remainder, but also in verifying for the factorization. If I would like to check for a linear polynomial to be a factor of the given polynomial p of x, I can simply do that also equally using remainder theorem. So let's see how we can use remainder theorem in factorization. Remainder theorem versus factorization. It's very simple to understand the factorization using remainder theorem. So let's see how we can connect factorization with remainder theorem. As we have discussed about remainder theorem, let's recap the definition or the statement of the remainder theorem back again. If a polynomial p of x is divided by a linear polynomial x minus a, it gives us the remainder p of a or f of a, is what we understand. If I get the remainder to be 0, then let's see what will be the special case. If p of a is 0, that is a is the 0 of the polynomial p of x, 0 of the polynomial p of x, which gives us a different concept of understanding the factorization. Therefore, if I have a special case which says p of a is 0, that is with the condition that the remainder is 0, that is when the a is the 0 of the polynomial p of x, then simply when I substitute this value in the remainder, I get remainder as 0. And when the remainder is 0, it comes under special case in the remainder theorem. So in the special case of the remainder theorem with remainder 0, that implies I say this x minus a is a factor of p of x. It acts as the factor of the p of x. X minus a is a factor of p of x. It exactly gets divided with the polynomial p of x. Is how we understand the factorization, then condition related with the remainder theorem. Is how I understand the factors connected with remainder theorem. Now let's take an example problem to understand the concept more better. Remainder theorem versus factorization. If I have a question which says, is x minus 3 a factor of p of x equals x squared minus 5x plus 6. I have a question here which says, is the linear polynomial x minus 3 a factor of p of x equals x squared minus 5x plus 6? Then how do we continue with? Of course, with the remainder theorem. Remainder theorem not only helps in finding the remainder, but also in identifying or justifying whether a given linear polynomial is a factor or not a factor of the given polynomial p of x. So let's see how we can do this with an example problem. As I have the given polynomial to be p of x equals x squared minus 5x plus 6 and my linear polynomial which is x minus 3, I clearly see the condition 1 of the remainder theorem which says the degree of p of x is 2, which is not equal to 0. The condition 1 where the degree is non-zero. And the second thing I find here is my x minus 3 when compared with the factor x minus a clearly says that my a is 3, which belongs to real numbers. So degree being non-zero and the value a belonging to set of real numbers is what is the condition for existence of remainder theorem. Now with these two conditions, let's see what is the remainder for the given polynomials divided one by the other. By remainder theorem, which we have already discussed in the session, if the polynomial p of x is divided by x minus 3, that implies the remainder is f of a or p of a, which is 3. Let's see what is the value of p of 3. P of 3 is when we substitute the value of x equal to 3 in the polynomial in the left side, equally on the right side with 3. 3 squared minus 5 times 3 plus 6, which on further simplification gives me 9 minus 15 plus 6, which is 15 minus 5, which is equal to 0. Therefore, my remainder is, when we cancel, I get as 0. Therefore, the remainder is 0. So when the remainder is 0, we have already discussed in remainder theorem connecting with factorization that if the remainder is 0, then the given divisor is a factor or a pure factor of the given dividend. Therefore, x minus 3 is a factor of p of x. It exactly divides is how we understand x minus 3 is a factor of p of x. Is how we conclude the remainder theorem with factorization. Remainder theorem also helps in finding factors and helps in finding the remainder. So let's see what are the factors for this given problem. So when I have the polynomial p of x, when divided by x minus 3, I have my p of x, which is x squared minus 5x plus 6 by x minus 3, which is x minus 2 times x minus 3. This polynomial is a quadratic polynomial or a quadratic function which can be expressed as factors by using factorization. When I factorize the quadratic function, I get the factors as 2 and 3, and therefore this can be written as x minus 2 times x minus 3 by x minus 3. It gets cancelled because it's a factor. And why is it a factor? Because it satisfies the remainder theorem with factorization. Remainder is 0, and hence, because the remainder is 0, the two factors get cancelled. That means x minus 3 is a pure factor of the given polynomial p of x, and the result is x minus 2. Is how we understand the complete concept of remainder theorem connected with factorization. Now that we have discussed about remainder theorem and its various significant facts in the branch of mathematics, let's enter into the next step of the theorems, the factor theorem. Continued from remainder theorem, today's session is about factor theorem. What is a factor theorem? The significance is what we are going to discuss before discussing the theorem itself in its own definition. The importance of factor theorem in the branch of polynomials is that factor theorem helps us in factorizing the polynomials. Remainder theorem helps us in identifying or justifying for the given linear polynomial to be a factor of the other polynomial, but factor theorem helps me in finding the factors directly. Finding out the factors or factorizing the given polynomial is what is the main significance of factor theorem. Let's see how it is possible. The theorem says that if I have, say for example, a polynomial p of x, which I need to factorize. The question here says factorize the polynomial p of x equals x squared plus x minus 12 is how I have this polynomial. So let's see how we can factorize using the factor theorem. Directly through an example problem, let's try to understand the concept more stronger. So in this case, my given polynomial is p of x equals x squared plus x minus 12. It is a polynomial which is non-zero, and I would like to factorize this or express as the product of the linear polynomials. So let's see how we can factorize this given polynomial. Now this quadratic polynomial has its coefficients which are 1 and the coefficient which is 1, and here the coefficient which is negative 12. So I initially pick all the coefficients or the constants from the given polynomial. So once I pick, I extract and identify for that for this given polynomial the coefficients are 1, 1 and minus 12. So with this concept, I take the middle one. The middle term is always the coefficient of x. Now here, the first condition in identifying the polynomial, the quadratic polynomial or any other polynomial in factor theorem is that I make the coefficient of x square always 1, or the highest degree coefficient should always be made equal to 1. Now this is directly out here with the coefficient as 1, so we need not just make the coefficient 1. Or for example, in case I have 2x squared plus 6x minus 9, then I try to make the coefficient of x squared 1 by taking 2 common, and I get this to be x squared plus 6 by 2x minus 9 by 2. Is how we take the 2 out and then make the coefficient of x squared or the coefficient of the highest degree polynomial equal to 1. Is how I understand the factor theorem condition. So once we satisfy the condition of the coefficient of x squared or the coefficient of the highest degree term being made equal to 1, I try to extract the coefficients. Then the middle coefficient, which is 1, and the last two coefficients, which are minus 12 times 1 is minus 12, is what helps me in factorization. So once I multiply the first and the last factors, I get the value as negative 12. Now the possible factors of minus 12 are minus 1, minus 3, plus or minus, plus or minus, plus or minus, and plus or minus 4. And this is minus out here. So I get the possible factors to be plus or minus 1, because 12 by 1 is a factor of 12, 2 is a factor of 12 with plus and minus both, and 3 is a factor, 4 is a factor, 6 is a factor, and equally 12 is also a factor. So I have possibly here 6 different factors for minus 12 is how I identify the factors. So once I identify the possible factors, then randomly I try to substitute each of them into the polynomial until the value becomes 0. So out of these, I identify the zeros. So which of the polynomials are the zeros is what we're going to identify here. So let's check if this is the 0 of the polynomial. P of 1 squared plus 1 minus 12 is minus 10, which is not equal to 0. Therefore, 1 is not the 0 of the polynomial. Even minus 1 also doesn't. So we randomly try with 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4, 6 minus 6, and 12 minus 12. And then whichever is the 0 of the polynomial, that value is picked, and that helps us in factorizing through the factor theorem. Let's try with 2 or minus 2. I get minus 2 whole square plus minus 2 minus 12. 4 minus 2, 2 minus this, again not equal to 0, is what I get here. So here it's again not a 0 of the polynomial p of x given. Let's try with 4 and 3. P of 3 is 3 squared plus 3 minus 12. 3 3 is 9, 9 plus 3 is 12, 12 minus 2, 12 is 0. And yes, P of 3 gives me the 0 of the polynomial. Therefore, x equal to 3 is the 0 of the given polynomial P of x. So I pick this. Next, let me try with 4. Minus 4. So when I pick for minus 4, I get this to be minus 4 whole square plus minus 4 minus 12. 16 minus 4 minus 12 is 0. And therefore, even minus 4 is picked. So and so forth. Randomly we go with each of the value of 6, minus 6, 12, minus 12, and then pick the zeros. And here for the polynomial, the zeros being p of 3 and p of minus 4. Even 6 and minus 12 does not give 6 plus or minus 6 and plus or minus 12 does not give the zeros of the polynomials. Therefore, 3 minus 4 are the zeros of the polynomial p of x. Now these being zeros, therefore x minus a is what we have seen in the remainder theorem. If the remainder is 0, then x minus a is a factor of the given polynomial f of x or p of x. So x minus 3 and x minus of minus 4, that is x plus 4, are the factors of p of x. Therefore, my p of x, which is x squared plus x minus 12, can be written as the product of the factors x minus 3 into x plus 4, is how I understand factorization through the factor theorem. Factor theorem is based on zeros of the polynomial. So for the given polynomial p of x, I just make the rule 1, that is coefficient of x squared should always be 1. Coefficient of the highest degree term must be 1, and the rest of the terms can be non-1. Pick the coefficients, multiply the first and last, find the possible factors. For each of the possible factors, identify which are the zeros of the polynomials. Pick those zeros of the polynomials and use the remainder theorem. Then we get the linear factors to be x minus a, x minus 3, and x minus of minus 4, x plus 4 to be the factors of the given polynomial p of x. And therefore, that polynomial p of x can be written as product of those two identified factors through the factor theorem. Factor theorem helps us in factorizing the given polynomial. Factorization through factor theorem. Now let's see a factor theorem applied example problem using the same concept for a polynomial with a higher degree. In the previous session, we have discussed about a polynomial which is a quadratic or with degree 2. Let's try the similar concept through a polynomial of degree 3, a cubic polynomial. So using the factor theorem for, say, a question where I need to factorize the polynomial x cubed minus 6x squared plus 11x minus 6. So let's see how I can factorize this cubic polynomial using the factor theorem. So let me go with rule number 1, where I'll write the polynomial p of x as x cubed minus 6x squared plus 11x minus 6. My first rule is to identify that the coefficient of the highest degree term is 1. So as I identify here, the highest degree of this polynomial is 3 and its coefficient is obviously 1. So I need not make it 1. It's already available with coefficient equal to 1. Is the rule number 1 in the factor theorem. So now that the rule 1 is satisfied, I pick all the coefficients 1, minus 6, 11 and minus 6. So I pick all the coefficients of this given polynomial and then I take the first and the last. My first and last coefficients are multiplied so that 1 times of minus 6 is equal to minus 6. So I get my product of the first and last term is what I do in the rule 2 of the factor theorem. So rule 2, multiply the first coefficient with the last coefficient and I get the value as minus 6. Now for this minus 6, I find all the possible factors for minus 6. As we know that plus and minus 1 is one of the factor for minus 6 and then plus or minus 2 is the possible factor for this. Plus or minus 3 is also the possible factor for minus 6, and plus or minus 6 is the possible factor for minus 6. So I have totally the 4 sets of possible factors: plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Now once the rule 2 is satisfied, now comes the next rule about finding the zeros of the polynomial. Using these possible factors, I next find the zeros of the polynomials. To find zeros, in order to find zeros, I just substitute the values in the polynomial, so that when I take 1, when substituted in the polynomial, let's see what would be the possible factor. So when 1 is substituted out here, I get this to be 1 cube minus 6 1 square 11 times 1 minus 6, which on further simplification gives 1 minus 6 plus 11 minus 6, which gives me 12 minus 12, which is 0. Therefore, 1 is the zero of the polynomial because it gives the value 0 when substituted in the polynomial. So one of the polynomial identified here with 0 is x equal to 1. Next, let's see how we can proceed further with this. Now let's try with the second possible pairs of factors, plus or minus 2. So I pick one of the sign, that is plus 2, and see if that is the zero of the given polynomial p of x. So I get this to be p of 2, which is 2 cube minus 6 times plus 11 times minus 6, which on further simplification gives 2 cube, which is 8, 8 minus 6 times 4, which is 24, and plus 22, which is 24 minus 24, because this gives me minus 30, and 24 plus 8, and therefore I get this to be 22, 11 times 2 overall, which gives me 0 on complete simplification. Therefore, I clearly identify that even x equal to 2 is the linear factor, or x equal to 2 is the zero of the given polynomial p of x. Similarly, I try with the other pair. P of 3, when I check for the zero of the polynomial 3, I just substitute p of 3 and I get this to be 3 cube minus 6 times 3, 11 times 3 minus 6. And this on further simplification gives 3 cube, which is 27, minus 6 threes, which is 18, 11 threes 33 minus 6, which on further simplification gives 27 plus 33, which is 57 60 into the square. So 6 times 9, which is 54. So I get this to be 27 minus 54 plus 33 minus 6, which is 54 plus 6, 60, 37 plus 27, 60. So 60 minus 60 also equally gives me 0. And therefore, even 3 is the zero of the polynomial p of x. Similarly, we try to test randomly through even 6. And then finally, because the degree of the polynomial is 3, I search for 3 zero polynomials. So now that I got these 3 polynomial zeros, I just directly have the remainder theorem, which says if f of x is 0 or p of a is 0, then directly we have x minus a is the factor of the given polynomial p of x. 1, 2, 3 are now the zeros of p of x. Now 1, 2, 3 are zeros of the p of x. Therefore, x minus 1, x minus 2, x minus 3 are the factors of p of x. These 3 are the factors for p of x by using remainder theorem. Therefore, p of x, which is x cubed minus 6x squared plus 11x minus 6, can be written as x minus 1 times x minus 2 times x minus 3 is how I get the possible factors. Finding the factors or factorization using factor theorem is possible for any polynomial of degree n. Now that we have discussed about the two important theorems, remainder theorem and factor theorem, now comes the new concept of the algebraic identities. Every part of algebraic identity is useful in solving many mathematical problems. So let's see what are the possible algebraic identities. Algebraic identities are the formulae which are said to be universally true for any variable. The left hand side will universally be equal to the right hand side, however be the value of the variable belonging to set of real numbers. So let's see some of the algebraic identities. The most important identity, as discussed in the lower classes, is that when I expand x plus y whole square, it must be universally equal to x square plus y square plus 2xy. Identity number 1 is how we see that this is universally equal to this, and this is true for all x, y belonging to the real numbers. This holds true for any variable x and y belonging to the real numbers. Similarly, I have the other identity which says that when I have x minus y whole square, it can be universally identical to x square minus 2xy plus y square for all xy belonging to the real numbers. Similarly, a plus b whole cube, a cube plus 3a square b plus 3ab square plus y cube. This is true for all x and y belonging to real numbers. Next, x minus y whole cube, which is x cube minus 3x square y plus 3xy square minus y cube, which is true for all x and y belonging to R. Next, x square minus y square is said to be identically equal to x plus y into x minus y, is how I identify the identity using x square minus y square equals x plus y into x minus y. Next, x plus a times x plus b by introducing the two new real numbers a and b can also be expanded and to be identically equal to x square plus a plus b times x plus ab, is how we identify for the two real numbers. For a and b belonging to the real numbers. Similarly, we have many other algebraic identities like x cube plus y cube, which is said to be x plus y into x square minus xy plus y square, is also one of the identity which makes this equal to this. X cube minus y cube is x minus y into x square plus xy plus y square, is how so on and so forth we have many algebraic identities. What if I have three variables introduced, x, y, z whole square? Then this also can be identified to be an identity, algebraic identity a square, x square plus y square plus z square, 2xy, 2yz, 2xz for all the real numbers x, y, z is how I identify the identity x plus y plus z whole square. What if I have x plus y plus z whole cube? This also has its own property. A cube plus b cube plus c cube plus 3ab into a plus b plus c cut. Now let's see the continuation of the algebraic identities. The next algebraic identity identified is x cube plus y cube plus z cube minus 3x yz is said to be directly equal or universally identically equal to x plus y plus z times x square plus y square plus z square is how we identify this example problem. Let's see how we can continue in identifying the applications of algebraic identities in solving mathematical problems. Say for example, I have a problem which says factorize 8x cube 27y cube plus 64z cube minus 48 144 xyz is what is the given problem, and I would like to expand to factorize this given polynomial in three variables x, y and z. So let's see how we can factorize this polynomial which is in more than one variable x, y and z being the variables using the concept of the algebraic identities. Now the given problem, which is 8x cube plus 27y cube plus 64z cube minus 144 xyz, can clearly be written as 8x cube, which is 2x whole cube, plus 27y cube, which can be raised to 27 being 3 cube, 3 times 3 times 3 can be written as 3y whole cube, so that this becomes a number, the perfect cube of 3y. And similarly, I have 64, which can be written as 4 cube, and this can be written as 4z whole cube. So the given polynomial can be expressed as 2x whole cube plus 3y whole cube plus 4z whole cube minus 144, which can be split as 3 times 2x times 3y times 4z. I can split this 144 xyz as 3 times 2x, which is the first term of inside the cube of the first term, and then 3y, which is inside the cube of the second term, and 4z, which is inside the cube of the third term. And then the reason why I expand and put it into this form is with the algebraic identity which is identified here. We know that the algebraic identity x cube plus y cube plus z cube minus 3xyz is identically equal to x plus y plus z into x square plus y square plus z square minus xy minus yz minus xz. So using this algebraic identity, I compare the left hand side of this identity with the given problem. Now clearly I see that in place of x I have 2x, in place of y I have 3y, in place of z I have 4z, so that this whole left hand side of the algebraic identity can be equally substituted for the right hand side of the algebraic identity, where my x, which is 2x, I have my this 2x with y with 3y and my z with 4z which comes in the first factor, x plus y plus z, and then x squared, which is 2x whole square, and y square, which is in place of y 3y whole square, and my z, which is 4z whole square, minus xy, your x being 2x and my y being 3y and z being 3z are equally substituted for x, y, z in the main algebraic identity. So 2x 3y minus 3y 4z minus 2x 4z is what we get when we expand through the formula. This can be further simplified so that I get this to be the first factor being 2x plus 3y plus 4z, and my second factor being 2x whole square, which is 4x square, and 3y whole square, which is 9y square, and my 4z whole square, which is 16z square, minus 2 times of 3, which is 6. Therefore, I get this to be minus 6xy minus 4 3 is 12. So I get this to be 12yz, and 2 times 4, which is 8. Therefore, I get minus 8xz is what I get as the factors for the given polynomial. Factorization of the polynomials which have more than one variable is done using the algebraic identities. This algebraic identity helps in factorizing this given problem. Applications of algebraic identities is to factorize the polynomials. Now let's see the other types of applications of the algebraic identities in solving many mathematical problems. As we have seen with the previous case of one of the algebraic identity which helps us in factorizing, the algebraic identities also help us in solving many problems which involve multiplication of two numbers. So let's see one of the application. The applications of algebraic identities is the topic for today's session. So for example, I have a question which says, find the product of 104 times 96. Then we can do this by using the calculator or with general multiplication, but without using the simple multiplication process, also we can just multiply the two numbers using the algebraic identities. Interesting, but yes, it can. Let's see how. Let's take the given product which needs to be simplified. I have this to be 104 times 96, which I need to multiply. So in order to do this, what I do is I try to express this in one of the algebraic identity form so that I can use it as a formula, and then the simplification becomes easier. So in this, generally what we do in these kind of problems is that we try to express through the standard numbers. 104 I can express in standard form as 100 plus 4, so that this 100 is easy to multiply or even to divide or add with other number. So the standard base here being 100 is taken for 104, so that 104 is written as 100 plus 4. This stands as the standard fixed number taken out here. Similarly, 96, if I express through the standard form, I can write it as 100 minus 4. So 96 can be written as 4 units short or 4 numbers short of 100, and 104 is 4 numbers ahead of 100, and therefore 104 is 100 plus 4 and 96 is 100 minus 4. The reason behind writing in this form is that we strike seeing this in the form x plus y times x minus y. We all know that x plus y times x minus y is identically equal to x square minus y square, or a plus b times a minus b is a square minus b square. Therefore, I get this to be a plus b times a minus b. Using this formula, I get this simply 100 square minus 4 square is what is obtained through the algebraic identity x plus y times x minus y is identically equal to x square minus y square. And this comes out to be 100 square is 10,000 minus 16. So I get this to be 100 square, which is 10,000 minus 16, which 9984 is the answer. Therefore, I get the answer to be 9,984. Therefore, 104 times 96 is 9984. This is very interesting because without using the general multiplication process, I can find the product of two big numbers using algebraic identities. This being one of the example case. Now let's see if this value as obtained through the multiplication of two numbers using the algebraic identity is verified to be true. Let's do the verification process by using the general multiplication of two numbers. As clearly we see here, I see that 104, when I multiply with 96, I get this to be 6 times of 4, which is 24, and 6, which is 2. 6 ones, 6. Next, 9 fours, 36, 9, 3, and 9, which when added gives me 4, 8, 9, and 9. And this comes out to be 9984, and this comes out to be 9984. Therefore, verification is true, is what I make the learning outcome. The learning of the product of two numbers using algebraic identity is very much true as compared to the general multiplication. Applications of algebraic identities in real life. Say for example, I have another set of an example which says simplify the value 99 whole cube. How do I simplify this without generally multiplying the numbers 99 times 99 times 99? Of course, we can simplify this using the algebraic identities. Let's see how we can use algebraic identities to solve this particular cube number. Now, as we see the question, I would like to simplify this 99 cube. Then clearly I write this to be 100 minus 1 whole cube, as discussed in the previous example, that we take the standard number as the base. So here the fixed standard number is 100, which is taken to convert the given number 99 in terms of 100. Therefore, the 99 cube can easily be written as 99 for 100 minus 1 whole cube. Now, once this is converted into 100 minus 1 whole cube, we see that immediately it gets compared with the identity x minus y whole cube. What is x minus y whole cube? It is an algebraic identity which expands to a cube minus 3a square b plus 3ab square minus y cube, or this can also be written as, this expansion is also equal to a cube minus b cube minus 3ab into a minus b. Both are the same expansions. Or this formula can also be written as x cube minus y cube minus 3xy times x minus y. Both mean the same identity for x minus y whole cube. So I'm going to use the second form of the identity for expanding x minus y whole cube, that is 100 minus 1 whole cube, indirectly 99 cube. So let's see how the expansion proceeds. So x, I treat 100 as x and I treat 1 as y, so that this gets reduced to x cube, which is 100 cube minus 1 cube minus 3xy into x minus y is what we get when we expand the given expansion. The 100 cube is 10 lakhs minus 1 cube is 1 minus 300 times 99 is what we get, which on further simplification gives us 1 lakh, 10 lakhs minus 1 minus 9 3s 27, 9 3s 27, 29 of 0, which further simplifies to give minus 29701. Now we need to subtract these two numbers to get the value for 99 whole cube. As we know that the subtraction of 10 lakhs is what we get when we subtract this number from this. Therefore, my answer for 99 cube, which is multiplication of 99 3 times, is directly 970,299 is what we get as the value using the algebraic identity. Applications of algebraic identities in solving the problems, the math problems in real life.